Good morning, Dr. Joel. So our team chose team 1, which is Smart Campus Monitoring System. So our team member, including me, Desmond, Gomesh, Govin, Chiang, and Jordan. So this is the table of contents of our presentation slide. So I will be handle background and motivation and project objective. Then Gomesh will do scope and data set use. Then Govin will do training process. Then Chiang will do the user interface and final outcome. Lastly, Jordan will do the summary and recommendations. Next. So our project is inspired by growing interest in smart campus and the role of intelligent monitoring in managing traffic and parking more efficiently. So at a university like Swinburne, where parking and vehicle tracking can be a daily challenge, having an automated vehicle monitoring system could be very beneficial. We decided to focus on detecting and classifying car models, especially the 5 most common sold in Malaysia. The main user of our AI system would include campus security and management staff, as well as researchers exploring smart city infrastructure. It could also support students in the future through smart parking apps or guidance system. The main objective of our project is to develop a deep learning-based system that can accurately detect and classify 5 specific car models using image taken on campus. We are focusing on real-world challenge by trying to answer a few key questions. First, what are the most common vehicle type we see around the campus? Second, we want to test whether the model perform well under real conditions, including occlusion, different lighting, and angles. And finally, we want to evaluate whether identifying the exact car model is the best approach, or if a broader classification like vehicle type might actually work better in practical application. So that's all for me. And now I will pass it to Gomesh.
Thank you, Desmond. Now we'll talk about the scope of this project. This project will consist of 5 classes of different car models, which are Perodua Beza, Toyota Vios, Perodua Myvi, Toyota Atlas, and Honda Civic. Firstly, one member will be doing the data preparation, where he will look for the training images online and annotate them using RoboFlow. Next, the second member will be labeling the class to assign the class ID for different classes and label the folder accordingly. Then, member 3 will be training the dataset with different car models and then fine-tune it until getting the desired output. Then, member 4 will testing the model with image taken in Swinburne and show the confidence value. Lastly, member 5 will integrate a UI which can upload the images for car model detection. Next, for dataset use, we will be using split the dataset into 3, which is training. Out of the 200 images, 162 images are used for training. This dataset is used to train the model so it can learn the pattern or images of the car model. Next, 18 images are used for validation. This dataset is used to tune the hyperparameter and monitor the overfitting. And lastly, 20 images will be used for testing the model. This dataset is used to assess the model performance in detecting the car model. Next, I will pass to Govin.
Thank you, Gomesh. Now I'm going to talk about our model that we used for training our dataset. So we have used YOLO V8, and the images were first annotated in RoboFlow, and the annotated images with their corresponding TXT files were exported in PyTorch format so that we can use it to train the model. So the reason why we exported in PyTorch format is because it is compatible with YOLO V8. So one class ID is given to one car model, and there will be a total of 5 classes. The model was first trained with YOLO V8s.pt, which is a pre-trained model by YOLO V8. Multiple models were trained by adjusting the number of epochs, enabling early stopping and fine-tuning previously trained models. To identify the best performing model out of 5 models, the MAP at 0.5 and MAP at 0.95 values from each model were recorded and compared. So this is the model comparison. We have used 5 different models to test out and see and choose which is the desired model that we like. As you can see, car model underscore YOLO V8 was the best model out of all 5 as it has the highest MAP at 0.5 and highest MAP at 0.95 value. The lowest performing model is the blur underscore car underscore model underscore YOLO V8, which has a MAP at 0.95 value at 0.5 value of 0.97191 and an MAP at 0.95 value of 0.94787. As you can see here, this is a comparison between the blur car model YOLO V8 output versus the car model YOLO V8 output. On the left side, the model could not identify the Toyota Vios properly, but on the right side, it could identify both the Toyota Vios and a Peroda Vesa with a decent confidence value. Thus, car model underscore YOLO V8 was chosen as the final model. Now, I'm going to pass on the presentation to Chi Yang.
Thank you, Govin. Now I will present the user interface that we have created. As you can see in this image, the left side is the input side, which enables the user to upload their images in the format of both .jpeg or .jpg or .png. While the right side is the output side, which will show the vehicles detected on the images. Next, I will talk about how to create the user interface for vehicle detection. To create this UI, we use Hugging Face website to connect with Gradio. Inside Hugging Face, there are 3 files required to be included, which are best.pt, requirements.txt, and app.py. Best.pt file is the train model file from YOLO VM model. It contains the learn wave used to make prediction on the input images. The requirements.txt file consists of a list of Python packages needed to run the application. So the Python packages will be downloaded after running through this code so that the function used in app.py can be run properly. Lastly, app.py is the main application script which as shown in the image. At the beginning, the YOLO VM model will be loaded, which is set in the best.pt. After that, a detect function is created to detect the vehicles on the input image. In the demo variable here, the Hugging Face is integrated with the Gradio website and design the UI. The launching function is very important at the bottom here because it is used to execute the function created. Lastly, we have obtained our final outcome. The end outcome will be shown like this. The user interface will be successfully detected the vehicles on the input image. There are bounding boxes and class labels accurately drawn for each vehicle, which are Peroda MyV and Peroda Beza. Confidence values for each vehicle will be displayed on the bounding boxes. And that's all from me. Next, I will pass the floor to Jotham.
Thank you, Chiang. So right now, I would like to do the summarize and provide recommendation and improvement. So for the summarize, the project used deep learning YOLO VX to detect and classify 5 common car models on Swinburne Sarawak campus. And the target car models include the Peroda Beza, Peroda MyV, Toyota Vios, Toyota Altis, and Honda Civic. And each class consists of 200 images, that 180 from online and 20 from campus. and the images were annotated using RoboFlow and exported in PyTorch format. And the dataset split into 162 for trend, 18 for validation, and 20 for test image per class. And the testing images were captured physically on campus for real-world evaluation. The trend model successfully detected vehicles with correct labels and bounding box, and the confidence value were displayed on the output of each detected car. And the simple user interface was developed using Gradle to run predictions and visualize the result. And for the recommendation and improvement, in the first, we have expand dataset diversity. It collects more images under different lighting, weather, and angles to improve model robustness and accuracy. And for the second one is to include more car models. We can add additional car models to make the system more versatile and applicable to broader use cases. And the third one is to enhance the user interface. We can improve the UI by adding features like video input, image history log, and result export option for better usability. And the last one, which is the deploy for real-time testing. Implement the system in a real-time environment, for example, like live CCTV or something else, to assess performance under actual conditions. So this is all of our presentation. Thank you.